Atoms, ions, and isotopes, oh my! Today we take a look at the three different types of particles and differentiate between them. How do atoms differ? There are over 110 elements on the periodic table, and according to Dalton, they're all different. What makes an atom of one element different from an atom of another element? So if I take a look at my periodic table, what makes, say, hydrogen over on the left-hand side different than, say, atom over here on the right-hand side? We already know that an atom is mostly empty space, that all the positive charge and the mass can be found in a very small, dense space that we call the nucleus. We know that there's positive charges, there's negative charges, but what specifically about an atom of hydrogen makes it so different than an atom of carbon? The answer lies in the atomic number. Henry Moseley discovers that atoms of each element contain a unique positive charge. Now we already know based on Rutherford's experiment that the positive charge can be found in a small, very dense place inside of the atom called the nucleus. That positive charge is determined by the number of protons, and it also identifies an atom. So the most important thing that you'll write down today is that the number of protons inside of a nucleus identifies an atom. Over here on the left, you'll see the symbol Mn, which stands for manganese. On the top, you'll see the number 25. That represents the atomic number, or the number of protons that an atom has inside of its nucleus. The number on the bottom is the atomic mass, 54.94 atomic mass units, and we'll talk a little bit more about that in the future. But what I want you to know is that every single manganese atom has 25 protons sitting inside of the nucleus. So its charge is a positive 25 inside of the nucleus. Every single manganese, 25 protons. If there aren't 25 protons, if there's, say, 3 protons inside of the nucleus, then it's not manganese. It has to be a different atom. And if you look at the periodic table, an atomic number 3, that is Li for lithium. So all lithium atoms have 3 protons. The periodic table that you see is organized by increasing atomic number. So on the far left-hand side, hydrogen's atomic number is 1, which means it has 1 proton inside of the nucleus. And if you look on the right-hand side, you'll see helium with the number 2. That means it has 2 protons inside of the nucleus. And as I keep reading from left to right, I'll see that protons or atomic numbers increase by the number 1. Because atoms are neutral, what conclusion can you make about the atomic number and the number of electrons? I hope you said that the number of electrons must be equal to the number of protons in a neutral atom. If an atom is neutral, it means that it does not have a charge. So for the element Pb, which is lead, it has an atomic number of 82. Remember, the atomic number represents the number of protons. So to fill in this table, we would put in the number 82 for number of protons. And because it's a neutral lead atom, I would also fill in the number of 82 for electrons. Next up, part B on this table, I have 8 protons. So we're going to look at the periodic table and we're going to find the element who has atomic number 8. It's one of the more popular elements. Symbol O, element name oxygen. Its atomic number is 8 and the number of electrons is also 8. The very last one here is 30 electrons. If there are 30 electrons, there must be 30 protons for a neutral atom. And if there are 30 protons, that means the atomic number is also 30. I'm going to look at the periodic table. I'm going to find element number 30, and that is Zn for zinc. At the bottom, we see the shorthand composition for each element and the table above. Shorthand composition is where we put the atomic number at the bottom of our symbol and the mass number on the top. We'll actually do a little bit more with that later on. We have one more particle to describe, and that's an ion. What exactly is an ion? And your definition is a charged particle. Now, based on what you wrote about protons, electrons, and neutrons, if I have a charged particle, which two subatomic particles have to be different in order to have a charged particle? And your answer is that the number of protons and electrons have to be unequal. So protons have a charge of +1, protons +1, electrons are -1. So if these two numbers are different, let's say that there are 6 protons. If an element has 6 electrons, it's neutral, it's an atom. But if it has 6 protons and say 8 electrons, it's not neutral anymore. Now there are more negative charges than there are positive charges. So in this case, if I take a look here, because I have 2 more electrons than protons, there would be an overall -2 charge. This would be a negatively charged ion. So the only way an atom can have a charge is if number of protons and electrons are unequal. But can the number of protons for an element ever change? I'm hoping you're screaming at this point that the answer is no. The number of protons is what identifies an element. So if an element has 6 protons, it is carbon. It has to be carbon. That's what makes it carbon. So the only thing that can be added or removed in order to have a charged particle has to be the electron. So if I change the number of electrons, if electrons are added or if electrons are removed, I have created a charge. So if you have your own device, I want you to play around with this PhET simulation. If you go to PhET Sims, and that's P-H-E-T, PhET, and then the next word is Sim, S-I-M, and then you put in the title Build an Atom, you'll see the sim that's here below. And what this sim allows us to do is to play around with the subatomic particles. It allows us to create neutral atoms, charged particles, and isotopes. Here are the questions that I want you to be able to answer after you finish playing with the PhET sim. What happens if you add protons to the nucleus without adding neutrons? Why does that occur? How many electrons fit into the first energy level? How many fit into the second energy level? Describe the general structure of a stable neutral atom. And last, describe the general structure of a stable ion. The last thing that you're going to put into your notebook is the following atomic structure, and this is for lithium. I want you to document the number of protons, the number of neutrons, and where the electrons can be found. You're going to fill in a pen chart. You're going to tell me number of protons, electrons, and neutrons. You will tell me whether this is a neutral or charged particle. You will determine the mass, and then you'll write its shorthand composition. To refresh your memory on shorthand composition, that's where we put the symbol first. I'm going to do hydrogen, so I would do the symbol for the element. On the top, I would put my mass number, and on the bottom, I would put my atomic number, which would also be 1. Maybe hydrogen was a poor example. Let's do a different one. Let's do instead nitrogen. So I would put the symbol, mass number on top, 14, and atomic number on the bottom, 7. So you will complete the 5 tasks on this slide in your notebook to conclude your notes. Here's one more example with oxygen. You can do the same activities as before. Fill in a pin chart, label as neutral or charged, determine the mass, and write the shorthand composition. Next up is mass number. Recall that protons and neutrons have a relative mass of 1 and electrons have a mass of 0. Relative mass meaning that for every 1 proton, the mass of a neutron is nearly equivalent. The next thing that I want you to know is that the mass number that you see is equal to the number of protons plus the number of neutrons. And that's really important, so I want to make sure that you have time to write that down. Mass number is equal to number of protons plus number of neutrons. Again, remember from Rutherford's gold foil experiment that all of the mass and all of the positive charge is found inside of the nucleus. So mass number basically is just the mass of the nucleus. And I'm going to make myself that note here too, that mass number or protons plus neutrons is really just the nucleus. How heavy is that nucleus? Electrons, their mass is so teeny tiny. We say it's basically 0. Also recall that Dalton was incorrect in saying that all atoms of an element are identical. All atoms of elements must have the same number of protons and electrons, but numbers of neutrons may vary. Now recall that neutrons don't have a charge, they are neutral. All they have is a mass, so they have a mass of 1, very similar to the mass of protons. In fact, we say their relative mass is 1 to 1. So we know that the overall role of a neutron is to stay inside of the nucleus. So what you see down here over on the right-hand side is the nucleus of a carbon-12 atom. So what I'm noticing is that there are 1, 2, 3, 4, 5, 6. There are 6 red protons, and there are 1, 2, 3, 4, 5, 6. There are 6 white neutrons. So the job of the neutron is basically, I like to call them like little middlemen. So the neutrons hang out in between the protons, because I know that positive charges repel. So the neutrons hang out in between the protons to keep them from repelling and to keep our nucleus from dissolving or breaking apart. Now carbon-14 on the right-hand side, it still has 1, 2, 3, 4, 5, 6. It still has 6 red protons. That's what identifies this as a carbon atom. But I'm noticing that it has 1, 2, 3, 4, 5, 6, 7, 8. It has 8 neutrons. So because it has 2 more neutrons than this carbon atom over here, take a look at what's happened to my mass number on the top. This one has a mass of 12, and this one has a mass of 14. So the mass has increased by 2 because I've added 2 more neutrons. So Dalton was very nearly correct when he said that all atoms of the same element are identical. The only thing that we have to change in order to correct that part of his postulate is that mass number can vary. Atoms with the same number of protons but different number of neutrons are called isotopes. And this is another very important definition. Atoms with the same number of protons but different number of neutrons are called isotopes. Isotopes will vary in mass, but because the number of protons and electrons are the same, they exhibit identical chemical properties. So again, I want to reiterate that the number of protons is what identifies an element. So if an element has 29 protons, it's an atom of copper. It has to be an atom of copper. Now the mass of that copper atom can change. I'm looking over here on the right that this copper atom has a mass of 63, but this copper atom has a mass of 65. So both copper atoms have 29 protons, but what differs is their overall number of neutrons sitting inside of that nucleus. So because the number of protons and electrons are the same for isotopes, they'll exhibit identical chemical properties. Isotope notation, each isotope is identified by its mass number, so you may see a few different options for isotope notation, and I've got them here at the bottom for you. So you can see the name of the element with a little dash and the mass number, so copper-63, or you might see the symbol dash and the mass. Those are fairly common. The last way that you might see them is, this is our shorthand composition, where you'll see the symbol and then the mass is a superscript right above it. So copper on the bottom, you put the mass on the top, 63, and then we can even go one step further and we can put the atomic number at the bottom, 29. A quick analysis of the 3 pictures below, and you can identify the differences between each isotope of the letter K, or element K, which is potassium. Take a quick look and analyze. Take a look at the number of protons for potassium 39, potassium 40, and potassium 41. All 3 of these atoms have 19 protons. Number of protons, identical for all 3. I'm also going to look at the number of electrons. All 3 have 19 electrons. So the only thing that's different between the 3 atoms that I see below, between potassium 39, potassium 40, and potassium 41, has to be that number of neutrons, 20, 21, and 22. And because the number of neutrons change, my mass also changes. So mass number, again, is simply what is the mass of the nucleus. I know all the mass can be found there. So if I take the mass of, let me get rid of some of my circles there. So if I want to take the mass of this first potassium atom over here, I'm going to take the number of protons and the number of neutrons, I'm going to add them together, and I should get 39. If I want to take the mass of this second potassium atom, again, I'm going to take the mass of, or I'm going to add the mass of the neutrons plus the number of protons, and I should get 40. And last but not least, I'm going to do the same thing for my very last atom over here, and I get a mass of 41. Mass number. Mass of protons and neutrons is about 1.67 times 10 to the negative 24th grams, i.e. very, very small. Mass of electrons, forget about it. Even smaller than that, too many zeros in front of that number to even count. Extremely small masses are really difficult to work with, so chemists compare it to a standard. We call that standard carbon-12. Carbon-12 has 6 protons and 6 neutrons, 6 electrons. It has a mass of exactly 12 atomic mass units. So because we know that the mass of an atom is just the mass of the nucleus, and that nucleus is only protons and neutrons, if it's carbon-12 and I have 6 protons and 6 neutrons, and if I add that mass together, I get exactly 12 atomic mass units, we can conclude that the mass of a single proton or neutron is very nearly 1 atomic mass unit. And you can look at the table down here below and look at the masses of each individual subatomic particles. Proton and neutron are extremely similar. Now there are some tiny differences, they're not identical, but when we round using significant figures, we're going to go and call those 1 atomic mass units. Our electrons, they are itty bitty. Their mass, they do have mass, but it's so small again, we're just going to go and call that 0. So to conclude, electrons have a mass of 0 atomic mass units, protons have a mass of 1 atomic mass unit, and neutrons have a mass of 1 atomic mass unit. And here's the overall question. If atoms have whole numbers of protons, neutrons, and electrons, why does the mass number have so many places to the right of the decimal? So if you take a look at the mass numbers on the periodic table, they all go several places to the right. So carbon, for example, is 12.011. Oxygen is 15.999. Phosphorus, 30.974. Where do all those places to the right of the decimal come from?